Throughout history, humanity has relentlessly pursued progress, pushing against the perceived boundaries of what's possible. From the simplest tools to the most complex machines, our ingenuity seems boundless. Yet, for all our advancements, we are now confronting an invisible, yet undeniable, wall, the very physical limits of our technology. This isn't about engineering a better design, it's about the fundamental laws of the universe dictating how far our digital creations can go. And in this confrontation with the absolute, a radical new paradigm emerges: quantum computing. It offers a glimpse into how we might not just meet, but perhaps even circumvent, these ultimate frontiers of human capability. To grasp the significance of this frontier, let's first simplify the current state of computing. Imagine a classical computer, at its heart, as an immense classroom populated by a group of 7-year-olds. Each child is tasked with answering basic math questions, operations literally simpler than first-grade arithmetic, simple additions, subtractions, ones and zeros. But gather a sufficiently large assembly of these young minds, and their collective processing power becomes staggering. This bunch of computational units can calculate anything from the intricate equations of astrophysics to rendering the vast, interactive worlds of a video game like Zelda. At the very core of every traditional computer lies the bit, the smallest indivisible unit of information. A bit can exist in one of only two distinct states, either a 0 or a 1. Visualize this as a simple light switch, either off or on, representing these binary values. This elegant, straightforward principle has underpinned the entire digital revolution, enabling us to encode, process, and transmit gargantuan volumes of data. For decades, the relentless quest for enhanced computing power translated into making these bits, and the transistors that control their states, progressively smaller, cramming ever more processing capability into shrinking physical spaces. However, this persistent drive for miniaturization is now encountering a profound and unavoidable obstacle. We are rapidly approaching a genuine physical barrier to our technological advancement, a limit imposed not by our engineering skills or inventiveness, but by the very laws of the universe. The components within our modern computers, specifically the transistors, have shrunk to an astonishingly minute scale. We are talking about dimensions where they are barely larger than a few individual atoms. At this incredibly tiny size, the classical laws of physics, which govern our everyday world and form the basis of our current machine designs, begin to falter and break down. When transistors achieve the minuscule size of just a few atoms, electrons, the fundamental carriers of digital information, start exhibiting highly unusual behavior. Instead of adhering strictly to their predefined pathways, these electrons can unexpectedly tunnel through what should be impenetrable blockages. This phenomenon, known as quantum tunneling, is a quintessential characteristic of the quantum realm. It effectively means that the precise, predictable flow of information, which is absolutely critical for the reliable operation of classical computers, can no longer be guaranteed. In this bizarre quantum environment, regular computers simply cease to function correctly. The quantum realm operates under a set of rules that are profoundly different from, and often counterintuitive to, the physics governing our macroscopic world. It is a domain where particles can seemingly exist in multiple locations simultaneously, where the very act of observing a particle can alter its state, and where our classical understanding of cause and effect often fails. Our existing computing technology, meticulously engineered based on classical physics, is fundamentally ill-equipped to navigate or effectively harness this alien landscape. The inability of classical bits to reliably operate at these atomic scales forces a complete re-evaluation of our approach to computation. This is precisely where quantum computers transition from a theoretical concept to a compelling necessity. To circumvent these profound physical limitations, quantum computers introduce an entirely new foundational unit of information, the qubit. Distinct from classical bits, which are confined to a definite 0 or a 1, qubits harness the perplexing properties of quantum mechanics. While they can still be set to one of two values, their inherent quantum nature allows for far more intricate states and relationships. This provides a revolutionary new method for encoding, processing, and manipulating information, fundamentally transcending the binary constraints of traditional computing. Quantum computing represents far more than just an incremental enhancement, it signifies a complete and fundamental technological shift. These machines operate on principles that are profoundly unlike the traditional computers we utilize every day. They leverage the unique rules of quantum physics to address issues that are inherently too complex, or even outright impossible, for classical systems to solve. Where conventional computers rely on a deterministic, step-by-step flow, quantum computers delve into a probabilistic universe of possibilities. This entirely novel paradigm promises a technological revolution with immense potential, offering unprecedented computational power for challenges currently beyond our grasp. It's crucial to understand that the term quantum computer encompasses different architectural approaches. Many discussions, including seminal explanatory videos on the topic, primarily refer to what are known as gate quantum computers, which process information using quantum logic gates in a manner analogous to classical computers. However, other distinct types exist, notably the D-wave machines. These are not gate quantum computers, they are specifically categorized as quantum annealing machines. The precise class of problems that quantum annealing machines can solve efficiently, or whether their capabilities are truly superior to classical machines for all problems, remains an active and evolving area of scientific inquiry. Despite ongoing debates regarding their exact theoretical computational advantages, D-wave machines have undeniably demonstrated significant practical capabilities. Research has concretely shown that a D-wave machine can achieve asymptotically faster results compared to the well-established simulated annealing algorithm, a powerful classical technique used for optimization problems. This compelling evidence strongly suggests that the D-wave machine is indeed effectively executing the quantum annealing algorithm itself, providing a tangible and measurable advantage for specific types of complex computational challenges. This highlights the diverse methodologies within quantum computing and the specialized strengths each approach may offer. The profound impact of quantum computing is projected to extend across an immense breadth of human endeavors. From accelerating the discovery of new drugs and advanced materials in medical science, to optimizing intricate global supply chains and logistics, its immense computing power holds the potential to fundamentally transform numerous sectors. The horizon also includes significant advancements in artificial intelligence and the development of novel, potentially unbreakable cryptographic codes, promising to reshape digital security and data processing. This technological revolution, once fully mature, could redefine what is computationally achievable, unlocking solutions we are only just beginning to envision. Major technology companies, such as Google and Amazon, are not simply observing this monumental shift from the sidelines, they are actively plunging into quantum computing with significant investment. Their motivations are clear and compelling. Imagine server infrastructures that are not only exponentially smaller but also dramatically more cost-efficient than anything conceivable today. This goes beyond merely reducing physical footprints, it's about unleashing entirely new levels of computational capacity that could power the next generation of cloud services and AI breakthroughs. Furthermore, the potential for patents and licensing this cutting-edge technology presents immense financial opportunities, making it a strategic imperative for global tech giants. For the typical home user, the immediate, direct impact of a quantum computer might not seem instantly revolutionary. It's indeed true that a quantum computer sitting quietly under your desk likely wouldn't offer a significant improvement over your current machine for everyday tasks like browsing the internet or playing video games. However, the true benefits will unfold profoundly in the background. From an internet, cloud computing, and server processing perspective, we are destined to witness immense advantages. The foundational infrastructure that underpins our entire digital existence will become vastly more potent, efficient, and capable, subtly enhancing every online interaction we undertake. This transformative shift towards quantum computing mirrors earlier periods of profound technological evolution. We often reflect upon the nascent days of computing, when machines occupied the space of entire small buildings, and marvel at the incredible miniaturization achieved since. Similarly, challenges that once appeared insurmountable, such as the intricate hybrid identity issues faced by large enterprises adopting early cloud platforms like Office 365 around 2010, are eventually overcome as technology matures and new solutions emerge. New computational paradigms, like quantum computing, promise that many of today's perceived limitations will similarly recede, one by one, unlocking previously inaccessible possibilities. While brimming with promise, it is essential to acknowledge that quantum computers themselves will come with their own set of inherent limitations. They are not a universal panacea designed to solve every computational problem effortlessly. For instance, while it's conceivable that certain cryptographic codes could be broken by quantum machines, other more advanced codes would likely remain secure, thus pushing the frontiers of cybersecurity rather than rendering it obsolete. Furthermore, the technology currently grapples with numerous significant technical hurdles, ranging from maintaining quantum coherence to sophisticated error correction, all of which demand sustained global research and development to surmount. Even after quantum computing technology becomes more widely accessible, it is widely anticipated to require substantial time to fully mature and realize its complete potential. The significant limitations and formidable challenges currently confronting its development are far from trivial, necessitating continuous and dedicated advancements in research and development across the globe. Nonetheless, the overarching trajectory is unmistakably clear. Quantum computing is positioned to instigate revolutionary changes across diverse industries in the coming years. This progression fortifies our conviction that quantum computing is not only a possibility but will fundamentally reshape the entire landscape of our technology. So, where truly lie the ultimate limits of human technology? And can we, as a species, find ways to navigate around or even transcend them? Quantum computers offer a profound and compelling answer. By meticulously understanding and ingeniously harnessing the enigmatic rules of the universe at its most fundamental, subatomic level, we may not just reach but actively redefine those limits entirely. What was once considered computationally impossible is slowly, deliberately, being brought within the expanding grasp of human ingenuity. This endeavor is more than mere engineering, it's a profound journey of exploring the very nature of information and reality, continually pushing the boundaries of what it means to compute.